All right, today we are going on a quest. A bit of a statistical adventure, if you will. We're going to take a big, messy pile of data and try to find one single number that can speak for the entire group. It kind of sounds like magic, but really it's just about knowing which tools to use.
So just imagine you've got pages and pages of information, maybe the lengths of fish or the sizes of different fungi. How do you boil all of that down? I mean, if someone asks you, so what'd you find out? You can't just hand them a spreadsheet, right? No, you need one number, one hero number that tells the whole story. And this whole search, this hunt for that one special number, is what statisticians call finding a measure of central tendency. It sounds kind of fancy, but all it really means is we're trying to find the heart of our data. What we're really looking for is a value that's sitting right there in the center of all our observations. It's a number that can basically stand up and say, hey, over here, this is what a typical value in this group looks like. It's like a single ambassador for the entire dataset. So, our first tool for the job is definitely the most famous one. It's something you probably use all the time, maybe without even thinking about it. We're talking, of course, about the mean. The mean is basically the workhorse of statistics. It's super straightforward. You just add up everything you've measured, and then you divide by how many things you measured. Simple, right? Let's see it in action. Okay, so let's put this to the test. We've measured the caps of 5 different fungi, so we've got 5 different diameters. To find the mean, the very first thing we do is add them all together, which gives us a total of 41.9 centimeters. Next up, we take that sum, 41.9, and we divide it by the number of fungi we measured, which was 5. And there it is. We get our mean diameter, 8.38 centimeters. A nice, tidy, single number, job done. Or is it? Because this is where our story takes a little bit of a turn. As useful as the mean is, sometimes it can be really, really misleading. See, here's the mean's fatal flaw. It's incredibly sensitive to extreme values. Just one number that's way out of line, what we call an outlier, can literally grab the average and pull it in its direction, giving us a totally warped picture of what's typical. Okay, take a look at this data. We've got 7 traps set for wood ants, and most of them caught a pretty reasonable number of ants. 4, 8, 9, all the way up to 25. But then you get to trap number 7, and whoa, it caught 202 ants. That trap must have been the place to be that day. Now, if we just go ahead and calculate the mean for this data, we get 39.3. But just pause for a second. Think about that. Does 39.3 really feel typical when you look at that list of numbers? 6 out of the 7 traps caught way fewer ants than that. Something's not right. This chart just shows the problem perfectly. You can see that little cluster of normal data points down at the bottom, right? And then there's that one giant skyscraper of a bar. That's our outlier. And look at where the line for the mean is. At 39.3, it's been physically dragged away from where most of the action is. The mean is just not representing this group very well at all. So when the mean is getting thrown off by an outlier, what do? Well, we call in a different kind of hero, one that isn't so easily influenced. Let's talk about the median. The median is really elegant because it's so simple. It is just the middle value. But, and this is the absolute key, you have to line up all your data points in order first, from smallest to largest. That's the one crucial step. So let's go back to our ant data. First, we arrange the numbers in order. Then, we just find the number that's physically right in the middle. With 7 data points, the middle one is the 4th in line, which is 12. Now notice how the median just doesn't care about that huge outlier. That 202 could be 2 million, and the middle number would still be 12. Now that feels like a much more typical value for these traps. And just real quick, what if you have an even number of data points? Then there's no single middle value. No problem at all. You just find the middle pair of numbers, and then you calculate the mean of just those 2. That result is your median. Simple as that. Okay, we've got one more tool in our kit. The mean finds the average. The median finds the middle, but the mode? The mode answers a totally different question. What's the most popular? Yeah, the mode is simply the value that shows up more often than any other. So if you want to know the most common shoe size that's sold or the most frequent score on a test, you are looking for the mode. So here, we're looking at the lengths of 100 different plant shoots.
If you just scan down that frequency column, you can see which length appeared most often. The number 74 millimeters showed up 19 times, more than any other. That makes 74 our mode. And visually, this is super easy to spot on a histogram. The mode is always just the tallest bar. It's the highest peak in your data's landscape. It's that most common value, just standing tall above all the rest.
And a quick side note on that, a data set can have just one mode. We call that unimodal, but sometimes you might see two distinct peaks. That's bimodal. You could even have more. The number of modes tells you something interesting about the actual shape of your data.
So we have our three tools: the mean, the median, and the mode. The real skill here is knowing which one to use and when. It's all about choosing the right tool for the right job.
So think of this as your cheat sheet. You want to use the mean when your data is pretty symmetrical and doesn't have any of those wild outliers. You switch to the median when your data is skewed by extremes, like with our ant traps. And you use the mode when your goal is simply to find the most popular or common value. Knowing which one to grab is everything. So learning how to find the center of our data is a fantastic first step. It really is. But the center is only half the story. The next big question is, how spread out is the data around that center? Are all the values clustered tightly together, or are they scattered all over the place? But that's a story for our next explainer.